Let's say that you have a function on the right. I showed an example of a function, lots of different ways that you can see a different function. So let's say that you have a function and you want to find the average rate of change between A and B. So the way that you're going to find that is by finding the slope of the line between A and B. So this one right here, this point right here is when x equals A. This point right here is when x equals B. So the average rate of change between those two values is going to be the slope of the line, or change in y over change in x. So I'm going to write delta y over delta x. So that's how you usually have seen it. You've seen it as y2 minus y1 over x2 minus x1. I'm actually going to show it to you in the way that you see it in precalculus and calculus. So this point right here, this y value right here is my f of a. And then this y value right here is f of b. Sorry that this is really messy. So in order to figure out the rate of change between a and b, we're going to find the slope of that line. And to find that, we're going to do f of b minus f of a over b minus a. So f of a and f of b are my y values, a and b are my x values. And this formula is going to be something that comes up again and again. You're going to use it extensively throughout calculus. You're going to use it in any sort of class where you do the application. For those of you that are taking physics right now, or have taken physics in the past, you might realize that this equation, if you have a position graph, this is actually the same thing that you do to find the average velocity. So that's one application of it. In math, we're going to just do it for the average rate of change. By the way, we often have constraints. So one constraint that we have is that a is not equal to b. If that happened, then your denominator would be 0. Your slope would be undefined. So we're not going to have an undefined rate of change. So one thing that I do want to mention is that this line right here is what we call our secant line. We're going to talk a little bit more about our secant line in a few minutes, but right now let's do a few examples with average rate of change. For our first example, we are finding the average rate of change of f of x equals 2x cubed from 1 to 3, and then also from negative 2 to 0. You do not need to draw a picture for these. However, I always like to draw a graph just so I can see what things look like. So I know that the graph of y equals x squared, or 2x squared, is going to look kind of like this. So I just drew a very quick sketch. You don't need to draw anything really, really well labeled or a really good sketch unless you either think it'll be really helpful for you or if you're asked to draw a nice graph. But this, I just sketched it. So our average rate of change for these, first of all, from 1 to 3, you can keep in mind that from 1 to 3, it'd be like this point all the way. It's going to end up being something way, way up there. Probably not so, probably more like that. So it's going to be like a straight line that has a positive slope. We know that our average rate of change is going to be the slope of that secant line. So it's going to probably be a positive number. You can kind of use, that's why I like to draw the picture, because I kind of use that to help me figure out how my answer is going to look. That way, if I get something like a negative number, or if I get a 0 or something like that, I know that I maybe made a mistake. Okay, so my average rate of change. My formula, again, is right above. From 1 to 3, the 1 is going to be my A, The 3 is going to be my b. So I'm just going to use that formula. I get f of 3 minus f of 1 over 3 minus 1. And I know that you can plug it in on your own if you want. F of 3 ends up being 18. F of 1 is 2. 3 minus 1 we know is also 2. So your answer for this one is going to be positive 8. That's actually all we have to do for this problem. If you have a word problem with these, you will have units. By the way, this question has been asked many times on the AP Calculus test. So if you understand this, you already know how to do one of the problems on the AP Calculus test. So good job. Okay, next one. We have the average rate of change from -2 to 0. That one's going to be kind of like, it's going to look about like that. You'll notice that it has a negative slope. So hopefully our answer ends up being negative. If it's not negative, we might want to check our work. So our average rate of change, by the way, unfortunately we don't have a variable to write this shorthand. I sometimes write it average AVG, but other than that, there's no real easy way to shorten it. So my average rate of change here is my A is -2, my B is 0. So I'm going to have f of 0 minus f of -2 over 0 minus -2. F of 0, if you look at our function, it ends up being 0. F of -2 ends up being positive 8. Because our -2 is squared. And then I end up with a positive 2 in the denominator. I get -8 over 2, which is -4. So if you look at the graph, it makes sense. It should be a negative rate of change at that point. So I mentioned previously, a secant line is a line that intersects 2 points on a curve. Here's a picture of a secant line right here. And our slope of the secant line, we often see written as m with a subscript of SEC for secant, is just going to be, again, as the previous one was, change in y over change in x. You can keep in mind this point is the x value is b, the y value is f of b, and this point down here, x value is a, the y value is f of a. So we do the same thing as we did previously to find the slope of the line, which means we're going to do f of b minus f of a over b minus a. I want to show you one other thing. I'm going to tell you right now, you're not going to be tested on it, but if you can understand this, you'll understand quite a bit of the stuff that you're going to need for calculus next year. So I think if you can understand this, it's great. So I want you to notice, I want to define the distance between A and B as h. So my first point right here is still going to be A, comma, f of a. The second point, however, is going to change to b is equal to a plus h, and then my f is going to be equal to f of a plus h. So what I can actually do is I can rewrite my equation right here as f of a plus h minus f of a over a plus h minus a. I actually can't do anything to the numerator of that fraction, so I'm going to leave it as is. But with the denominator, I can cancel out the a minus a, and that just gives me h. So I want you to look at this equation and think, does it look familiar? So I'm hoping that you maybe notice that this equation is almost the same thing as the difference quotient. If you didn't notice that, by the way, it's fine. But I do want you to know that actually the difference quotient that we were finding previously is going to also give you the slope of a secant line. So like I said, you're not going to be tested on it, but just kind of keep it at the back of your mind. It's something that's going to come up in future classes, especially if you take calculus at some point. So for this example, we are going to kind of apply the rate of change and what we just talked about with the secant line. So we are going to take this equation, f of x equals x squared minus 2x minus 3. We'll find the rate of change from x equals negative 2 to x equals 1. And we're also going to find the equation of the secant line containing these 2 points. We'll talk about the secant line one in just a second, but let's find the average rate of change. I forgot to write the word average in there, so you might want to add that in. Okay. So my average rate of change is going to be that formula I just had. So it's going to be f of 1 minus f of negative 2 over 1 minus negative 2. If you plug in the values, f of 1 is going to be equal to negative 4. F of negative 2 is going to be equal to 5. And then in my denominator, I get 1 plus 2, which gives me 3. So I end up getting negative 9 over 3, which gives me negative 3. So you might be looking at part B and be wondering, like, what the heck are they asking for? But actually, we're just finding the equation of the line containing, oops, wrong pen, containing negative 2, comma, f of negative 2. We just found f of negative 2. We figured out that it was 5. And then also 1, f of 1. We just found f of 1. We figured out that it was negative 4. So basically, we're just finding the equation of the line containing these 2 points. Now, you can go ahead and do everything that you have learned in previous classes for finding the slope of the line, the equation, or you can realize that we actually just found the slope of that line just a second ago. So my m in this case, we already know is negative 3. You do not need to do any extra work on this one unless you really, really like finding slopes, in which case, go ahead, find it. From there, you can find the equation of the line. I'm going to do it using point slope. You're welcome to do it using slope intercept. I've noticed most students prefer slope intercept, but I'm going to show you point slope in case you forgot it. So point slope, we have y minus y1 equals m minus x1. M times x minus x1. So I'll use this first point. You can use the second if you want to. I get y minus 5 is equal to negative 3 times x plus 2. That gives me y minus 5 is equal to negative 3x minus 6, or y equals negative 3x minus 1. So the last thing that you can do on this type of problem, and I highly recommend it, is to try to graph that equation, the original equation, and look at that line and see if it does look like it's a secant line. So I'm going to graph this. So I know that this line is a parabola. And one little tip on this is I already figured out that there's a point at 1, negative 4. And I also figured out that there is a point at negative 2, 5. So I know that I at least have those two values there. Actually, if you solve for the x-intercept and the y-intercept, you'll find there's a y-intercept at negative 3. And you'll find that there's an x-intercept at both negative 1 and positive 3. So you can do that. By the way, I know we haven't gone over using graphing calculators yet, but once you figure, if you have tried to use it, you can look at that. You can look at the graph there, or you can use Desmos online. Okay, so anyway, we are going to take a look at, so my secant line, would be between this point right here, -2, and -2, 5, and 1, -4. So it looks about like this. And you're going to want to look at that and see, does it make sense if that has an equation of -3x minus 1? Looking at it, it looks like it has approximately a y-intercept of -1. -3 seems like a reasonable slope, so actually it looks pretty good. You don't need to draw this every time, but it doesn't hurt. It's a good way to check your answer.